Hello, my beautiful and handsome students. Welcome to Science Tutorial. This edition of Science Tutorial is a special edition because it is designed to prepare students for their WASSCE, NECO SSCE, and also their UTME. So if you are preparing for any of these exams, it is important that you watch this program because it will help you in the preparation. Now, we are still on the concept of elasticity of materials, and we have looked at the meaning of elasticity, and we have also generated a series of equations that can help us do calculations or carry out calculations in elasticity. So if you watch our previous video on the concept of elasticity of materials, then you will actually understand where we started from. Okay. Today, we are going to look at force extension graph, the force extension graph. Now, we are going to do a little illustration using the practical aspect. Not that we are here to run the full practical, but we just want to do a little illustration based on what Ohm's law is all about. Now, this setup, this is a rotor stand that has a clamp and a hose, and this is a meter rule. This is a hanger for masses. We have different masses here. Because it's not a full practical class, we are not going to be having a table where we are going to place these masses. That's where we are going to record the masses at the end of the day, because we are not running a full practical section. So if we are running a full practical section, it means that we are going to tell you the value of our masses. And then this is a spiral spring. We will know the original length of the spiral spring. And we also know the final length. And finally, we find the extension by using the final length to subtract the original length. Remember, in physics practical, you always insert your unit on the table. You always insert the unit on the table. This is cm. So if we are to run this experiment, maybe if this is a practical class, that's what we are going to have. And we will now list the masses that we are going to use for the experiment, then record the original length. If you look at this, we have the pointer, the calibrated part of the meter rule, or the graduated part is actually facing you, that is watching this video. So this is a pointer that will actually show us the length at any point in time. It will be wrong if we don't have this pointer, because when you do this, the measurement will be wrong. So we need to use a pointer. We need to use a pointer. Now, if you remove this, remember, if you look at this now, you discover that this is the original length of this, because this hanger has its own weight. So if I release my hand, you see, it extended this. So this hanger has its own weight. So, but what we want to look at is just to see whether what Hooke said about force and extension, whether it's actually correct. You know, he told us that force is directly proportional to what? Extension. That means whenever there is increase in force, there is also increase in what? In extension. And what is acting as force now is this mass. The masses that we are going to use, they are the ones acting like force. They are the weight, because when we slot this mass here now, they would have weight because of the influence of what? Gravity. All right. So when we begin to, let's say I decide to slot a mass now from here, you will notice, you see that now the spiral spring extended. There is increase in the length of the spiral spring now, so there is extension. If I add another mass, the extension will continue to do what? Increase. Let's say I decide to slot another mass in here. Just notice that, you see, there is increase in length again, which you can actually measure. If this is a practical section, I will be measuring this length. You discover that as the mass or as the force is increasing, the extension will also be what? Increasing. So that's what Hooke says, and that's actually true, provided the elastic limit is not what exceeded. We saw that when we looked at Hooke's law. But it comes to a point where this proportionality that exists between the force and the extension, there is a point that it can stop. And that's why we want to look at the nature of the force extension graph, or the force extension curve. So when we have the practical section, you will see the full demonstration of this. But because this is a revision class, we really need to touch more on the theoretical aspect of this topic so that our students can actually know what to write in case they see questions like this in their exam. All right, so let's now focus our attention on the theoretical aspect. At least we have seen that when force increases, that the extension will also increase. Now, what is the nature of the force extension curve? What is the nature of the force extension curve? I'm going to draw the force extension curve, and we'll explain some points on that. Is the origin. Let's say here is the extension. The unit is meter. I don't have space by the side. Let me do this one. This is the force. The unit is Newton. Now, when we draw the graph of force against extension, we're going to have a graph that will move like this. So I'm going to level some points. I want to level some points. Let me call here B. Let me call here X. Let me call here Y. Let me call here E. Let me call here P. Wow. Now these points I have leveled, they are very much significant. Very, very significant in the force extension graph. Remember, anytime you are drawing graph in physics, just for you to, for emphasis sake, you must label your axis properly, and the appropriate unit must also be placed on your axis, like I've just done. I didn't have to, that's why I have to write the meter here. The unit of extension is meter, the unit of force is Newton. In some, if it's the real practical, we just use the symbol that was used for the values that you're going to plot on the vertical and also on the horizontal axis. Now, what are the significances of these points? I will look at the point, this region. If you look at this region, this is a straight line. Within this region, this point is a straight line. Let me draw that again. Okay. This is a straight line. What's the significance of that region? That region OP is called the proportionality region. Proportionality region. That's the region OP. Why is it called the proportionality region? It is the region that obeys Ohm's law. The region at which increase in force will also cause a proportional increase in the extension. So that region is called the proportionality region. Take note of that. Then we have the point we call E. Point E is the elastic limit. The elastic limit. That is the point where the material is elastic. Within that point, from here to here, at that point, from O to E, the material is still elastic. Immediately after the elastic limit, the material will lose its elasticity. So the elastic limit is a point beyond which the material will cease to be elastic. The elastic limit is a point beyond which the material will cease to be elastic. What it means is that after the elastic limit, the material will not be able to return to its original shape. So the elastic limit is the point beyond which, after that elastic limit, the material will no longer be elastic. So then we have the point we call Y. We call it the yield point. The yield point. The yield point is when the material has given up all its elasticity and now has become a plastic material. In other words, within this region, the material is no longer behaving like an elastic material, rather it's behaving like what? A plastic what? Material. So at yield point, all the elastic property in that material will be given up. There will be no elastic property again present in that what? In that material. Once we get to the yield point. Remember, immediately after elastic limit, plasticity begins. The material now starts behaving like a plastic material, but it can still have a little elastic property inside it. But once it gets to the yield point, at that point, it loses all its elastic what? Elastic property. It loses all its elastic property. That's why it's called the yield point. It has yielded to plasticity now. It's no longer, there's no longer an elastic property present in that particular material. Now we have the point S, we call it the maximum load. Maximum load or force. Maximum load or force. That is the highest force that an elastic material can withstand. So look at it, there's no force. If you trace this to the force axis, there is no force that is higher than this. Look at it, there's no force that is higher than this. So that's the maximum load. And finally, we have the breaking point. At least you from the name, you can actually tell us what it means, the breaking point. At this point, the material, there is possibility that the material will now cut or do what? Or break. That's at this point. All right. So these are the points and the region that are obtainable in the force extension curve. Now, I want to also say this, that from E to B, from this region, that's the plastic region. So at this point, the material is now behaving like what? Like a plastic. That's from E to what? B. So that's what we call the plastic region. Now, I want to move on to talk about this proportionality region. Supposing that Hooke's law is fully obeyed, you will notice that we are going to have a graph like this. Our force is F, right, in Newton. Let's say our extension is E in meter. If Hooke's law is obeyed, we are going to have a graph like this, a straight line graph like this. Okay, let's say a few things from this graph now. If Hooke's law is obeyed, remember this from that region now, they are not obedient to Hooke's law. That's why they are misbehaving. You see their misbehavior. They will just come down, go up, come down. They are just dancing up and down. But you see this man, he's an obedient man moving just straight. So if Hooke's law is obeyed, that's what we are going to have. Forget about these disobedient children. They don't understand what it means to be obedient. Don't mind me. Now, if Hooke's law is obeyed, we are going to have this. I'm going to make two important statements before we move on. One, if we decide to find the slope of force extension curve or force extension graph, the slope. You remember how we find slope? Okay. Now from here to here will be change in the force, and here will be change in the what? Extension. Now the slope now will be what? Change in the force, change in what? Extension. That will be the slope. Now this slope, the slope of force extension curve is force constant K. That's the force constant K. The slope of force extension curve is the word force constant. This is very important. So the slope, when you plot the graph of the force against extension obtained in an elastic material, the slope you are going to obtain is the word force constant. If Hooke's law is obeyed, remember that's how we started. If Hooke's law was obeyed in that experiment or in the practical. So the slope of this graph is the word, the force extension curve. Now another important statement that we need to drop is this. The area under the graph, let's say that we now have this, I think I can take away this. Hooke's law was obeyed here. On one side, this is where the graph stopped. The area under the graph will be this. That's this area. This area. It's going to be this. So it's triangular in nature. So that's this area. The area under this graph is the work done by the elastic material. So two important things that we're going to take home as far as the force extension curve is concerned, the force extension graph is concerned, if Hooke's law is obeyed. One, the slope of the graph will give us the force constant or the elastic constant. Two, the area under the graph will give us the what? The work done by the elastic material or the energy stored in the elastic material. Remember, it's still possible that the shape can change. We can have something like this. So this is the whole area. So we have it. This now look like as if it's like a trapezium or something. I can break it up here. This one is a triangle. This one is a trapezium. Now the work done in extending this in the whole of the graph is going to be the area of this and the area of this. So area under the force extension graph will give us what we call the work done by an elastic material or in an elastic material, or the energy stored in an elastic material. All right, let's drop a few more terms. That we need to take note of. Terms associated with elasticity. Terms associated with elasticity of materials. So we have few terms that we're going to draw. One is what we call tensile stress. Tensile stress is force per unit area. Tensile force, I can say, is force over area. Okay, I can use a symbol, what we may call sigma. Let this be my tensile stress. So I'm representing tensile stress with this F as force and A as area. Then we have tensile strain. Tensile strain or strain is extension over original length. So if the strain, I use gamma, you know that symbol, its extension is an original length L. That's my strain. That's my strain. Strain is extension per unit length. That's the original length. So that's beautiful enough for you. Now you notice that the unit of force is Newton, the unit of area is meter square. So the sigma, we have the unit of Newton per meter square. Newton per meter square, which is the same unit with pressure. Now extension is in meter, length is also in meter. They will cancel out, so there is no unit for what? For strain. Strain is dimensionless. Strain is dimensionless. Doesn't have units. There's no unit for strain. Now we have their elder brother we call the Young modulus. Young modulus is the ratio of tensile stress to tensile strain. We usually use E to represent the Young modulus. That means E now will give us tensile stress, which I have called this beautiful, call it sigma. You can draw it, you can develop your own symbol anyway, and then this is strain. We can go further to incorporate these two into this. What is stress? Stress is force per unit area. And what is strain? Extension per length. So Young modulus now, by the time you do the mathematics, F over A divided by E over L. That's, let's just illustrate that. That would be F over A times L over E. When you multiply this, you have FL all upon what? AE. Remember the mass, when you change division to multiplication, you invert the fraction after that sign. That's what we just did. Since we don't have unit for strain, so it means that Young modulus will take up the unit of what? Of tensile what? Stress. Tensile stress. All right. So far, so good. I believe that you are enjoying the revision class. So we just have a few more things to say, and then we'll say goodbye to uh, the concept of elasticity of materials, and then we'll focus our attention on the calculation now, because this is a revision class. So the next class we are going to have, we are going to do series of calculations in order to see how we can use all these expressions. But let me say this: when a material has a circular cross section, you see, circular cross section, the elastic material has a circular cross section. Now the area where the force is being applied will be on the circular surface. You see that? That's on the circular surface. So in that case, this area can be written in pi r square. Yeah, that's A. A can be pi r square. A can also be what? Pi d square all upon what? 4. So in case you have a question where they now substitute, when they give you diameter, that means you need to use that. So for circular cross section, we have that A is pi r square, which is also pi d square over 4, where r is the radius and what? D is the diameter. So I can possibly write that the sigma, that's the stress, to be force over pi d square over 4. And that can also be written as that as force 4F now, by the time you translate that, over pi d square. So depending on the variables or the parameters given in the equation, you now know what to do. So quickly, let's look at the work done, and then we'll end the class. So that next time we are going to continue with the calculation. So work done in an elastic material. The work done in an elastic material is equal to the energy stored in that elastic material. So the energy stored in an elastic material is also equal to the work done. So work done in an elastic material is equal to the energy stored. That work done, W, is given by the average force times extension. The average force times extension, that's the work done. Average force, F is force, E is extension. So the work done is average force times extension. So the energy stored is also average force times extension. That's the work done. But we can actually do a lot of transposition when we remember that F itself is KE. So if I use KE to replace F here, I will still say that work done will be half KE, which is F times E. And that will give me half KE squared. That's another expression for work done. That's work done. So if I'm given the force and the extension, I will use the first expression to do the calculation. And if I'm given the force constant and the extension, then I'm going to use what? The second expression. Supposing I'm given the force and the force constant from here, if I say that E is F over E, sorry, F over K, and I use the whole of this to replace E here, that's beautiful. I'm going to have a third expression that work done is half F squared over what? Over K. Yeah. So how many expressions can we use now? 1, 2, and the what? 3, depending on the variables that are available in the equation given to you. That's what will determine the expression that you are going to use. Now, finally, if you have a catapult, you know catapult, you can, the one they use in shooting lizard and the rest of them, that's a catapult. You know, when you, it's elastic, the rubber there, when you release it, the stone will leave with a particular speed. So the work done also, remember we said energy stored. So the energy can be potential energy, or can be kinetic energy. So the work done will also be linked to the kinetic energy and also the potential energy. So the work done in an elastic material, when there is motion, will equal to the kinetic energy produced. So in that case, I'll be having that half Fe is equal to half mv squared. Half can actually take care of half. Then you have Fe is equal to mv squared. So note this. Also, if maybe a body moved from a certain height and compressed a spring or compressed an elastic material, now the work done by an elastic material is also equal to the potential energy. In that case now, from a certain height, that will give me half Fe is equal to mgh. Wow, we have actually generated a lot of expressions starting from when we started this class, and there is need for us to master all of them, but never mind. We are going to actually see how we can apply these expressions. Physics is beautiful. Oh, very, very beautiful. Just take notes of all this. In our next class in this revision series, we are going to see how we can use all these expressions in calculation. But before then, we are going to list the expressions on one side of the board when we want to start the calculation, so that when we have a question from the list of the expressions, we can select a suitable expression or expressions, because in some cases we may need to involve more than one expression in order to solve a particular problem. All right, thank you for following the class to this point. Thank you very much. Keep watching science tutorial. Like our page on Facebook, follow us on YouTube, and also like our page, the Mathematics Meal page on Facebook, and also subscribe to our YouTube channel on Mathematics Meal 1, and you will not regret it. Thank you, and God bless you.